Hello, my name is Michael Lin, and I'm presenting my optional project that I made in Algodoo. So I decided to cover the topics of the conservation of mechanical energy, conservation of momentum, and then just the roles that some conservative and non-conservative forces play in the simulation. And I chose these because I noticed when I was playing around in Algodoo that it's really easy to keep track of the velocity and angular velocity and where energy is present and isn't present in the system. And so I realized that obviously velocity and energy is very important in the conservation of energy and in the conservation of momentum. So I decided to make a little simulation where I drop a ball and then witness a couple of collisions just to see where energy is conserved and to see where work is done in the system by both conservative or non-conservative forces. So I'll show you the simulation now. So here's the setup I made in Algodoo, and I decided to record it ahead of time and then voice it over afterwards so that I could grab the numbers from the simulations, do the calculations in my calculator, and then provide those values, the quantifications of energy in my voiceovers. So I also decided to have the force vectors on and the velocity vectors on initially, just so you could see what forces are acting on the objects that are moving and where they're rotating and traveling. And so for this setup, the ball is a half meter in diameter and it weighs 0.5 kilograms, and it's being dropped from a meter stick that is exactly 5 meters tall. That would mean the initial potential energy of the ball is about 24 joules. And so I'm going to drop the ball here completely frictionless so it won't roll, and I just wanted to see initially how perfect conservation of energy is in this simulation. So I checked, and the velocity at the bottom of the incline was 8.3 meters per second in a frictionless situation. And this means that the final kinetic energy of the ball is 17.2 joules, which is about 6 or 7 joules less than the initial energy of the ball before it was dropped. So this just shows me that Algodoo is not the perfect simulation tool. Obviously, this should have been a perfectly conserved situation, but it was not in the simulation. But I'm going to use the 17.2 joules as a reference point for the rest of the presentation, and that's where we'll see where energy is and is not conserved. So next, I'm going to turn friction back on for the ball and for the surface, and I just chose 0.2 as a good coefficient because that seemed about where it is usually in the problems we're doing in class. And so after setting the friction, we'd expect the ball to roll. And so you'll see the angular velocity vector appear now. And at the bottom of the hill, it was traveling slower than the before. It was only traveling 5.9 meters per second. And it did have an angular velocity though. And combined, we can use those to calculate the final kinetic energy of the ball. And here, it was only equal to 12.18 joules. And I think that it's about 2/3 of the initial value of what we would have expected in a perfectly conserved situation. But I think that we can chalk this up to two reasons, being the rotational friction, the rolling friction of the ball, and just the fact that friction is much more present now than it was before. And friction is a non-conservative force, so we'd expect some energy to be expelled from the system as the frictional heat. So I'll reset the system once again, and this time we're going to look at the spring at the end of the rolling ramp for the ball, and we'll see how energy is not conserved in that collision. Obviously, the final speed of the ball is much lower, and we see it's only going to be about 2.1 meters per second, or 1.7 meters per second, and clearly here, since the spring did not enact a perfect transfer of energy to the spring and back to the ball, and it kept moving because the spring is not perfect and not perfectly dampened. This just shows us that this is not an ideal situation where there's no friction or there's no non-conservative forces. So energy was lost in this situation. Next, I'm going to grab this block, and this block is 1.5 kilograms. Is 0.5 kilograms. So this will double the mass of the system once the ball strikes it, from 0.5 kilograms to 1 kilogram. And I'm going to first see how energy and momentum, then momentum, are acted on in this situation. So immediately after they collide, the new or velocity of the ball and box is 3.0 meters per second. And so in this, the energy was not conserved because in a collision where the objects continue moving together, we'd expect the kinetic energy to decline by a factor of 2 if they have the same mass. And this is about where we are. So the final velocity of 3 meters per second gives us a final system's energy of about 5 joules. And this is about half of the initial 12. It's not perfect, but that is roughly where it should have been. And as for the velocity, or the momentum was in fact almost perfectly conserved. The initial momentum of the ball was 2.95 Newton or kilogram meters per second, and the final momentum was 3. So there was barely any discrepancy in momentum before and after the collision, which is what we wanted to see. And now I'm going to add wind into the situation, which is a non-conservative force. So I have it at 20 meters per second squared acting against the direction of the ball. And you'll see at the bottom of the roll here, the ball has about half a meter per second less of velocity than it did before. And this is just because here some kinetic energy has been lost to the environment since the non-conservative force of wind is acting on the ball while it rolls. And in fact, I did the calculation and it looks like about 0.05 joules of work was done by the wind, which is a very small amount, but it's enough to lower the kinetic energy of the ball. And in the final situation, I'm going to look at how dropping the ball and as it rolls under a motor, we'll see if the motor does some work on the ball. So I'm going to drop the ball, and the velocity of the ball here is 6 meters per second, like it was before. And after it strikes the motor, the velocity is 7.9 meters per second. So that means that the motor did 6.6 joules of work, because work is the change in kinetic energy. And we'll look at this one more time just to see how you can visualize the work that was done. So clearly, when the ball strikes the motor, it speeds up quite a bit.
Thank you for paying attention to my presentation in Algodoo. I had a lot of fun making this, and I wish I could go more into detail and do more trials and run even more calculations, but obviously I don't want to take up all the time just looking at things in Algodoo. But I really enjoyed being able to see the actual numbers behind the collisions that I was watching. So being able to see the velocity and then do the calculations to see how energy is conserved and where momentum is conserved, and then try and figure out what's causing the discrepancy. And I thought that was really interesting, and actually Algodoo might be a helpful tool for me moving forward to talk about some of the things I don't understand right now in lectures with springs and pendulums. But obviously Algodoo isn't the perfect software. Since I just had a ball rolling, that was easy enough to model with the circle tool. But the springs I had a tough time making, and I would have loved to use the thrusters, but they're just a little bit tricky to use. But I had an easy enough time modeling what I needed to model, but I was definitely held back in what I could show in the simulation just because it is a little finicky. I wish I could see more data about the friction and the non-conservative forces acting, but I don't get to see any vectors for friction or any vectors for the wind force. So maybe in the future that would be something that I could investigate more. But other than that, thank you so much for your attention, and I hope that I was able to show you what I learned in Algodoo today. Thanks.